Hi everyone. I know I look kind of strange in my little window with all these lights here, but this is so that the compass right here can actually be seen. We're going to make some measurements of compass needle deflection when a current carrying wire is nearby. This video will serve the purpose of both the first part of the lecture that we did in class on Monday for Physics 206, as well as a pre-lab video, because we're basically doing the first part of lab this week for my folks in 176. It'll also help the folks that were in 206 lab that either already did this to refresh what happened, or the folks that are going to have 206 lab on Thursday. That's fine too. I have to remember I'm not looking into that. I'm looking at this one. So the first thing we need to do is talk about what this device is. So the compass right now is pointing geographic north, which is actually behind me. That's what a compass should do if used appropriately, and we need to realize that when we use a compass the right way, we are eliminating all other sources of magnetic fields so that it points north. What a compass actually is, let's get this video out of the way. A compass is actually, I like to think of it as a magnetic field detector. It will actually detect the net magnetic field in that region. Now, when the Earth's magnetic field is the only magnetic field, then the compass needle points north, right? That's the direction of the compass needle. However, if the compass needle twists a little bit, it's not that there is a new north, it's that there is a new net magnetic field. So if we know that north is, let's say, up and down in the page, so this is magnetic north, but our compass needle actually looks like this. Here is our compass needle. I'm drawing it red because the north end of the compass needle is red. I'm drawing the whole thing red though. At this angle theta, well, that could only happen if there is an additional magnetic field in green twisting that compass needle to the side. So we could call this B applied. Let's call it that. In black would be the magnetic field B of the Earth. And then the compass needle points in the net field direction. So our vectors, if we just look at vectors, we have B of the Earth, we have B applied, and then we have our compass needle pointing in the direction of B net. So a simple vector statement would be B Earth, right, plus B applied is equal to B net. And furthermore, the useful thing about this angle, what we can actually measure on a compass, because if we look at a compass, and I'll open that window back up, if we look at a compass, there are degree marks on it, right? We start at 0 degrees and we go all the way. This is 30. You can't see that here. I realize you're on this camera, but if we look down here, we have 180, and then we go up to 210, 240. Here would be 270, and so on. So we can measure that angle with the compass quite easily. And when we measure that angle, if we have a B applied that's relatively the same size as Earth, and that is we have an angle in the 20, 30, 40, 50, 60 range, not all the way at 90 or all the way at 0. We'll talk about why in a second. We can say that the tangent of that angle is equal to opposite, so B applied, over B Earth. And we typically know what the magnitude of the magnetic field of the Earth is. It's different depending on your latitude. The horizontal component of the field changes because it kind of pokes into the sphere at different angles. We give you that value in the lab though, and I am about to pause the video to get that value for you, but we can right here, B applied is equal to the magnitude of B earth times the tangent of that angle. So I'm going to pause the video to look up what we stated the field of the earth was in the lab. I'll be right back. Okay, so according to the lab handout, the Earth's magnetic field that we are going to use is 2 times 10 to the minus 5 Tesla times the tangent of theta. So we can determine the strength of some other field as long as we assume that it's perpendicular to the Earth's magnetic field. So our lab setup is going to necessitate that arrangement by taking 2 times 10 to the minus 5 Tesla, the Earth's magnetic field, the horizontal component at this latitude roughly, times the tangent of the angle that we measure on our compass. In order to understand this arrangement of field, Earth's field, and the field produced by the wire, let's first just explore, without taking any calculations, what the magnetic field of the wire must be shaped like using this same configuration, knowing that the deflection of the needle assumes that at least some of the field is pointing perpendicular to the Earth's field. So let's look at let me get back to here and open up our video here. Okay, so we have, again, this compass positioned so that the needle is pointing north. I've tried as best as I could to get the camera right over it so there isn't any sort of parallax error like that. And I have here, it's going to be off camera because I'm kind of zoomed in pretty tight on the compass, but I have our usual batteries and wires and a single bulb here that is going to supply, the batteries will supply current to this wire. The bulb is just so I can show you that when I clip the wire, the bulb is on and there's current running in the circuit. So the first thing I'm going to do is, with the bulb off, this wire has no current running in it. And when I take the wire and I put it, whoopsies, let me get that back on camera. I've got to be careful not to touch this too much. And I put the wire on top of my needle. Notice the needle doesn't do anything. So just having a conductor nearby does not make my compass needle twist at all. Now I'm going to turn the current on. So I was unplugged before. You can see the light bulb is not on. Now, aha, my light bulb is on. That light bulb is glowing brightly now. Current is running through the wire. And right now, current is running down through the wire. So let me make note of that. I'm going to pause the video so you don't have to watch me do this. So due to the arrangement of the batteries, current is now going to be running north for this wire. I have my current on. I just unplugged it while I was doing. Let me plug it back in. So current is on. And now with current running north, as I bring this wire down on top of my needle, you'll notice that it deflects. So I lift it up, it goes back to north, and as I bring it straight down, we see that that needle twists a little bit to the west. Well, that's interesting. So it must be that underneath the wire, thinking of that diagram that we had before, the Earth's magnetic field points in the north direction. There must be a field from my wire underneath it pointing to the west. Let's flip this around and lay the wire down and bring the compass on top of it. So let's switch this around. I'm going to lay my wire in the north direction, roughly north. I put my compass on top of it, and we see it deflects to the east. When I lift it up, I gotta get a grip on it, it goes back north. I bring it down, it deflects slightly to the east. It's a little bit of a sticky compass. East, goes back north, goes to the east when it's on top of the wire. That isn't as clear to see because there we go. Goes back north. On top of the wire, it deflects ever so slightly to the east. A little bit hard to see because I'm a little bit farther from the wire on this end. We can see it, at least when I lift it up, we see that needle swing back. I'm lifting it straight up, and that needle swings back to the north. So that means it's deflected to the east when the wire is below the compass. Now I'm going to flip this around. Now I'm going to keep my compass the same, but by switching my wire around, we're now going to have current running in the opposite direction. So let's get this back on the camera. So right now I'm going to bring my wire so that the current's running in the opposite direction, and I bring it on top of my compass. And now we see a deflection to the east there. Sticky compass, get back there. North and a deflection to the east. My compass needle is twisted down. Let me get another compass. Okay, sorry about that. My compass needle was tilted down and it actually wasn't pivoting freely. But now we can see, with current running in the opposite direction, when I bring my wire down, we see a deflection to the east. When I bring that wire down on top, and my current's running in this direction, south. So let's summarize all these things with some sketches, okay? Before we do that, though, actually, we'll summarize with the sketches first. So if we go to, do that one, good. I'm going to draw a nice picture of the wire. So here is my wire, and I'm going to draw it this picture somewhat three-dimensionally. This is my long, straight wire, okay? It's carrying a current. We'll say the current's in this direction, I. Now, if that current was north, we know that from our observations, deflected the needle below it to the west. So below this wire, we have a field that is to the west. Above the wire, we have a field that was to the east. When the compass needle was above the wire, the needle deflected in the other direction. And furthermore, when the when the wire flipped directions and the current was to the south, the field under it was in the other direction. So that corresponds to this picture as well. If we put together all of our observations, we actually get a field that looks around the wire like this. Let's take a point of view that is the following. Let's say that we're looking down the barrel of the wire, and let's say the current's going away from us. So we are standing facing north, and the current is directed to the north, which for us is into the screen. I realize I'm writing underneath my picture. Let me just move this. There we go. And the current's running into the screen as we're looking at it right now. Well, if the current was running into the screen, at a point below it, we saw a field that was west. Yep. So that's the direction of our field at a point below. At a point above it, we saw that the field was to the east. And there was nothing that we did that actually paid attention to how that wire was twisted, which means if we actually twirled that wire around, we get no different result. So that means that to this side, the field points up. And to this side, oh boy, I better add some more fields here. Give me a second. There we go. Oh, yeah. 2020, Jeff, come on. Hopefully most of you are, listening to this while you're doing something else. There we go. Now the picture's okay. So that field, it creates sort of a circular swirling field around that current carrying wire. So we notice the hallmarks of our observations above it and below it. The fields are in opposite directions. And if we picture looking at the current coming towards us, which was like when we flipped the wire around, then that field direction changes. Now below the wire, the field's in the other direction. So that looks like this. If the current was coming out towards us, so that would be a current like this. So now with the same convention, if north was into the screen, we'll say that now we're looking at a current. Let's make this just a little bit bigger. Current, excuse me, yes, a current. I drew the wrong letter. A current coming out towards us, which we'll say is south, so out of the screen. That is not a convention that north is into the screen and south is out. That is us just imagining that we're standing facing a certain direction for this discussion. Now, if the field is coming out away from us, we have the field at a point above the wire going off, whoops, to the west. Below the wire, the field is this way. And then around, I'm not going to draw it the same way I did before. So we have that, again, what we observed was just the above and below being oriented in such a way that it deflected the needle so that we could see it on our compass. Now, this does mean when we do the lab, we have to be sure that our wire is oriented north-south so that we can get a deflection that is due solely to the field of the wire being perpendicular to the field of Earth. One thing that the compass cannot show us is when the field is in the same direction as the field of the Earth, it can't show us how big that field is. Our ability to say that the magnitude, that the magnitude of the field of the wire is equal to 5 times 10 to the 5th times the tangent of theta, we can only say that when our field from the wire is perpendicular to the field of the Earth. So we can use that deflection to do that simple geometry. Our compass needle can only twist, right? If our field is so much larger than the Earth and it twists all the way to 90 degrees, well, a bigger field can't make the needle twist anymore, so we can't detect how big that field is. We're limited, right, by it being making the needle go 90 degrees. Similarly, if the field pushes on that needle that's already pointing north, I can't stretch the needle. So what we see if we go back to our wire and our magnet, right? Now we know, let's turn the circuit back on. Right now the circuit's off. I turned it off while I was talking. But now we know that and I'm going to switch my current around as well. So just, it's more comfortable to hold the wire this way, the way I have things set up. I get my compass to go back to its non-deflected, easy to read. Here we go. So now, when I have a current carrying wire that has the field wrapped around it, let's see, whoops. Turning my circuit on. Current's coming this way, this way, this way. Right? Okay, so that matches what we had before. That again, that field for this wire is wrapping around that wire. If you've seen the right-hand rule, you can think about it going with your thumb in the direction of current, curling around. If I hold the wire perpendicular, we see it doesn't deflect the needle at all. Because right now, the field from this wire is going this direction. It's pointing in this way. And you see that's not going to make my needle twist one way or the other. It's just going to put the needle in tension, right? If I flip it around, now it's going to want to stretch that needle out, but I can't see the needle twist because the needle needs to twist to show me that deflection. I can't see that stretching or compressing because the needle doesn't actually show that. So we do have to be really careful in lab to make sure that we are orienting our wires in such a way that we get this shape of the field. So for those of us watching this video, because it's part of your pre-lab, I know it's a little bit longer, but this is really the first part of the lab. Hopefully you can do this quickly when you get to lab. For those of us in lecture, this was about the first 15 minutes or so of lecture, and I've just recreated it for those of us that are watching it because they weren't able to be in class. Excellent work, everyone.